This graphic summarizes one of the most important things in chemistry, which is how to do molar conversions. You can try to memorize this graph, and I've seen people do it. It's really not hard. It's actually really good practice. But don't try to just memorize a graph and don't understand the actual math that's going on when you do these molar conversions. So let's do the first most common molar conversion, which is converting between mass and moles. When you have a mass, like 30 grams of water or whatever, and you want to find out how many moles that is, because all of these are just quantities, you're going to end up dividing by the molar mass. And then you can go the opposite direction. Same key, you're going to multiply by the molar mass if you want to convert from moles to mass. So that means that molar mass is our key to unlocking this bridge in both directions, and it has the units of grams per mole, which you can see contain the units for both moles and mass. Another common one is using number of particles. So to go from the number of particles to number of moles, or vice versa, particles just refers to atoms or molecules. It can also refer to electrons and photons, but just anything that's super small that can be very numerous. So to convert from a number of particles to the mole, you're going to divide by a special number called Avogadro's number, abbreviated in subscript A commonly. And to go the opposite direction, you're going to multiply by Avogadro's number in subscript A. That means that Avogadro's number is the key to unlocking this bridge between moles and number of particles. And Avogadro's number specifically is 6.02 times 10 to the 23rd particles per mole. So we see here that the units also contain both particle number and moles. And then lastly, this one's kind of specific, but you'll certainly see it. It's how to convert between the volume of a gas at STP and moles. STP refers to standard temperature and pressure, which is mostly understood to be 0 degrees Celsius and 1 atmosphere of pressure. So if you have the volume of a gas and you want to convert that into moles, what you're going to do is you're going to divide by a specific number, which is 22.4. To go the opposite direction, so to convert from moles to a certain volume of a gas at STP, you're going to multiply by 22.4. That means that the special key here that unlocks the bridge in both directions between the volume of a gas at STP and a mole is 22.4 liters per mole. So here we see that we have mass, gas volume at STP, and number of particles, all of which can connect to the mole. So you could go from mass to number of particles as long as you follow the steps of you would divide the mass by the molar mass to get moles, and then you would multiply that by Avogadro's number to get number of particles. This basically just summarizes the main molar conversions, but definitely try to understand it. We're going to use this chart to verify that each of these directions makes sense using dimensional analysis. Let's verify that this diagram makes sense by actually doing some molar conversions. Remember that the diagram is best used to summarize and review what you know, so let's learn how to do it using dimensional analysis. This question says, how many moles is 330 grams of nitrogen trichloride? So we can see here that we're going to go from mass toward moles. According to our diagram, that means we're going to divide by the molar mass. So let's see if we do that. We have 330 grams of the nitrogen trichloride over 1. I'm going to convert from the grams of the NCl3 to moles of the NCl3. We cancel out our units, and we see we have moles of NCl3 that survives. So let's actually put in our values. We have 1 mole of NCl3. If you calculate the molar mass, you get roughly 120 grams. So if we do our math here, we get about 2.75 moles of the NCl3. So we just converted grams to moles. Where did the molar mass go? The molar mass is down here at the bottom, which means that we actually did end up dividing by the molar mass. So this part here makes sense. Now let's go in the other direction. We're going to go from moles to grams. So what mass is 0.55 moles of glucose? We would start with 0.55 moles of glucose, so C6H12O6. And we would put a fraction bar, multiplication symbol. We're going to put moles of glucose in the denominator, C6H12O6. It can be repetitive writing these out, so you don't necessarily have to do that. When you get to stoichiometry, it might be advisable to write out the chemical every single time. So we're going to go from moles to grams. Cancel out moles, top and bottom, circle grams. That means that we're going in the right direction. We know we're going to use the molar mass because it does say that that's our key, and according to this, we're going to end up multiplying by the molar mass to get from moles to mass. So the molar mass of glucose, if you were to calculate it, is roughly 180 grams per mole. So if we calculate it, we get about 99 grams of glucose. So that seems to check out with what we are doing and summarizing with our graph or with our chart. Now let's see how to go between number of particles and moles. We can divide by Avogadro's number to go from particles to moles, and this says we can multiply by Avogadro's number to go from moles to particles. So we're going to try that out. The first question is, we have 2.46 times 10 to the 24 titanium atoms, which is a lot of titanium atoms. So 2.46 times 10 to the 24 atoms. I'm putting that over 1. I could put Ti as well, but I'm kind of tight on space here. You don't really have to do that because we're not changing particles. We know we're talking about just titanium here. Now, I can put atoms in the denominator because I need to cancel atoms out because I'm going from atoms, which is a type of particle, toward moles. So I can circle it there. So what we are doing with this first one is we're going from particles to moles, which means we need to have Avogadro's number in the denominator. But don't just memorize that from the chart. Understand where it should go. 1 mole of anything is 6.02 times 10 to the 23 particles, or in this case, atoms of titanium. When you do your math here, you're going to get about 4.09 moles of titanium atoms. You don't have to put all that extra stuff. At the end of the day, it's really just 4.09 moles of titanium. For number 2, this is kind of interesting, but these are methane bubbles that are trapped in ice. Methane is a natural gas with the formula CH4. Do you need to calculate the molar mass of methane? You certainly know how to. It would be the 12 for the carbon plus 4 times the 1 for each of those hydrogens. But it's really helpful to think about whether you need to do something before you do it when it comes to solving things in chemistry. Because we're not dealing with molar mass, we don't even need to worry about the molar mass of methane. So be careful when you're solving problems to save yourself time to not do what you don't need to do. So we have 1.83 moles of methane. I can put that over 1. To get rid of moles of methane, I'm going to put that in the denominator. And I'm going from moles of methane to molecules of methane. You can abbreviate molecules as MOLEC, or you can write it all the way out. Just don't abbreviate molecules as MOL or MOLE. That is already taken by moles, and they're not the same thing. So we can put CH4 here to be super complete if we want to. 1 mole of anything, in this case methane molecules, is 6.02 times 10 to the 23. So we're using Avogadro's number. Moles of methane cancels, molecules of methane does not. When we do our math here, we're going to get a really large number of about 1.10 times 10 to the 24 methane molecules. You don't have to put CH4 molecules. You can do it in either order, or you can just omit the CH4, but you do need to have units. And in this case, the units are molecules. So for number 2, what we did was we went from moles toward particles. And that explains why in number 1, we divided by Avogadro's number, as it says we should. But for number 2, we multiplied by Avogadro's number, just like it says we should. Now we're going to practice using the molar conversion that connects moles to gas volume, which is going to be this part of our diagram. We're going to verify that everything checks out. A container of helium contains 14.7 liters of helium at STP. Helium is a gas, and remember this number only applies to gases at STP. How many moles of helium is 14.7 liters of helium? So we have 14.7 liters of helium gas over 1. And I'm going to go and cancel out liters of helium gas. I'm going to put that in the denominator, liters of helium gas. And I'm going to convert that to moles of the helium gas. I like to be very explicit with how I label things usually so I don't get confused and whoever's reading it doesn't get confused. So that's why I put all the extra stuff after the L and the MOL. So 1 mole of any gas, in this case helium gas, occupies a volume of 22.4 liters of space at STP. So our units are going to cancel top and bottom here, and we're going to get a value of roughly 0.648 moles of that helium gas. And that is our answer. We converted liters to moles, and that's how we did it. Did we end up dividing by that special number? We did. So to go from liters into moles, we ended up dividing by 22.4, which is why it's in the denominator. Now we have another question. What volume of oxygen is 53.3 moles of oxygen at STP? So we start off with our moles, 53.3 moles of O2 gas over 1. And I'm going to convert that into liters. So to do that, I'm going to get rid of moles of O2 gas, which I'm going to put it in the denominator. I'm going to go to liters of the O2 gas. So 1 mole of any gas, in this case oxygen, is 22.4 liters of space at STP. We cancel out our units top and bottom and we circle this. And we get a value of roughly 1,190 with some sig fig rounding. And the units are liters of oxygen gas. So did we follow the rules here that were summarized by this chart? So we converted from moles to liters. To do that, we took our starting moles and we multiplied by 22.4 to get the volume of that gas at STP, which will be in liters by default. And yes, it checks out.